Cycle 3, Lesson 21, Part 2. This is the last lesson of Cycle 3, long cycle, and it's just more to do with trig identities, because there's a lot of varieties of trig identities, and the more you see, the more comfortable you'll become with them. So as you can see at the top is just a recap of some of the most commonly used trig identities, in particular the Pythagorean identity and the quotient identity. Those are our real go-tos. And of course the reciprocal identities we use whenever we see a reciprocal trig ratio, we should change it back into one of the primary ones. Also, compound angle formulas, most of the time, well, I don't know if I should say that. I was going to say most of the time we're starting with stuff that looks expanded and then putting it back into a more simplified looking version, because that is usually beneficial to us. Although, having said that, that's not always the case, as I think we're going to see in the very first example. Whatever version you see it in, let's put it that way, if you see a trig identity that looks like any of these, then for sure you should consider if it's helpful to change it to look like this. But going backwards might, just as likely be the case. If you see something that starts out looking like this, then consider going that way. There's only two ways to go, and whatever you start with, you might want to consider switching it to the other form. All right, so two examples in this short lesson. The first one is we want to prove that 2 sine x sine y is equal to cos x minus y minus cos x plus y. The more complicated looking side, which is what we always want to start with, is the right side. And so there we have it right above us. I'll write it out again just because that's what I do. So I have something to start with. So I've, in my own mind, clearly separated it so that it's its own thing. I'm just working on the right side is the way I think of it. Now we can see right above, if I scroll up a little bit, that cos x minus y is equal to cos x cos y plus sine x sine y. I can also see that cos x plus y is equal to, and I need brackets here to keep my signs straight, cos x cos y minus sine x sine y. When I take those brackets off, then the signs get simplified. The first couple terms, nothing happens to. I guess I left out the y in that line above. So there's y plus sine x sine y. So just rewriting these guys. But now I take the brackets off, make sure my signs are correct. This becomes a plus sine x sine y. And what you'll see is that we've got cos x cos y minus cos x cos y. They cancel out. And I've got sine x sine y plus sine x sine y, which becomes 2 times sine x sine y, which is what the left side of the equation, the identity, looks like. So there's our proof. So using double angle formulas again is one of our options. And in this one, we have a cos 4x minus sine 4x equals cos 2x. So on the left side, what comes to mind is a difference of squares. If I think of cos 4 goes to the cos x to the exponent 4 as just cos squared x squared, and likewise with the sine, then that's a difference of squares. On the right side, I can see that as a double angle formula, which I don't think we've got written up there, but remember there are a bunch of versions of the double angle formulas. And so if I just go back to those, let's see if I can find those quickly in our notes. Was it here? Yes, it was here. So remember the double angle formulas for cos 2x or cos 2 theta is equal to cos squared theta minus sine squared theta, or cos squared theta equals 1 minus sine squared theta. I guess that was just rearranged, but then simplified it was 1 minus 2 sine squared theta, and then the third version was cos 2 theta was equal to 2 cos squared theta minus 1. So those are all different versions of it. It might be hard to see how exactly that's going to become the left side. So let's work on the left side, because that gives me an opportunity to actually simplify things. Because what I can do is I can factor it as a difference of squares. And I think we'll see most clearly doing it that way, how it's an identity. But having said that, as you should know by now, there's not one correct way to do an identity. We can follow many different paths to prove it. As long as we're following mathematical operations, we're good. Anyway, if I take the square root of cos to the 4x, then the square root of that is just cos squared x. So I'll put that at the beginning of each of my factors. I know that if I do FOIL and expand this out, cos squared x times cos squared x would get me back to cos to the 4x. Likewise, the square root of sine to the 4x is going to be sine squared x. And I know since it's a difference of squares, I'm going to have a plus sign between one set of terms and a minus sign in the other bracket. Now, looking at this, we hopefully recognize that this is the Pythagorean identity. So that's equal to 1. So what I'm left with is simply 1 times cos squared x minus sine squared x, or just cos squared x minus sine squared x. And that was one version of our double angle formulas. That was the first version that we just looked at a moment ago. So that's equal to cos 2x. Cos 2x is equal to cos squared x minus sine squared x. And so we've proven, once again, that the left side equals the right side. And we're done. There's the practice questions. I'm not sure if that's all of them. I do, again, have it as a separate sheet. So let me see. There they are. Here's actually all the practice questions. So there's some practice questions here at the bottom of this page, but for the full selection of them, we need to actually look at a separate page here. But as usual, I've got full solutions here, so because that's helpful if you get stuck with trig identities. So you've got lots of resources